heat waves, drought, tornadoes, hurricanes, floods, blizzards, bitter cold. Extreme weather has an incredible impact on people across the globe. On Mount Washington, our scientists brave some of the worst weather on the planet to improve our understanding of our warming world. All right, hello and good evening. Welcome everyone to Mount Washington Observatory's Science in the Mountains with program support from MathWorks. My name is Brian Fitzgerald and I'm the Director of Science and Education here at Mount Washington Observatory. And joining us this evening to discuss the extremes of extraterrestrial weather is Mirka Zapletal, who is the Director of Education at McAuliffe-Shepard Discovery Center in Concord, New Hampshire. Thanks so much for joining us for tonight's program. For those of you who aren't already familiar, the Mount Washington Observatory is a nonprofit member-supported organization whose mission is to advance the understanding of the forces that create Earth's weather and climate. And we accomplish that through a few different ways. We operate our Summit Weather Station with around-the-clock weather observation and forecasting, by conducting research and product testing projects, and by developing and offering educational programs. So if you have questions for tonight's speaker and are joining us via Zoom, please use the Q&A button. You can find that at the bottom of your toolbar on your video screen. We're going to be able to collect your questions throughout the program, so put them in there as soon as you have them. And we'll have a live Q&A session at the end of the program, so make sure you get your questions in. If you're joining us on the live stream on Facebook, welcome and thanks so much for being with us. While we won't be able to respond to your questions in the Facebook feed during the program, our Summit staff will try to respond as quickly as they can afterward. If you'd like to connect with us through Zoom for the next program, please be sure to register using the program link on mountwashington.org/SITM. Alrighty, so thanks again, everyone, for joining us for the program this evening. Before we kick things off, I'm going to launch a quick poll here with some great trivia questions as well. So let's see if I can get these launched. And you should see some poll questions. For those of you who are on Zoom, you can take a look and enter some responses here. Several questions tonight, including, where are you joining us from this evening? Are you joining from, say, in our neck of the woods here in the Northeast, perhaps somewhere else in the country, or perhaps even outside the United States? Feel free and go ahead and let us know where you're joining from. Always curious. Also curious if there are any members of the observatory out there in the crowd this evening. I'm sure there are quite a few. And then we have some trivia for tonight, in which Mirka is going to be able to get to some of these questions, but we want to see what you all know already. So the first question being, which planet is the closest in size to Earth? And you have a few different options there. Next, Mercury's atmosphere contains all of the following except, and once again, you have some options: oxygen, potassium, calcium, argon. And finally, the strongest winds in the solar system are found on Neptune, Venus, Jupiter, or Triton. So get your responses in as soon as you can. Seeing quite a few responses already, so I'll just give it another 10, 15 seconds here. Already getting quite a few responses, so thanks everyone for participating. And we'll just wait another second or two here. Looks like responses are leveling off, and we'll end it in 3, 2, 1. All right, what did we end up with? So of the 141 of you who responded, overwhelmingly joining from the Northeast, thanks so much for joining, although we also still have a couple folks from outside the US. Got representatives from every single sector of the United States, more or less. Apologies for not including the territories. Perhaps we have some folks out in the territories. Members of the observatory, ooh, okay, about 50% are not members of our nonprofit organization. That's too bad, but thank you to all the folks who are current members, and for the 12 of you who said, no, you're not a member at the moment, but you will be following this program, so thanks so much. All right, and then, which planet is the closest in size to Earth? The majority voted for Venus, then Mars, then Neptune and Titan. Mercury's atmosphere contains all the following except quite a few of you, the majority selected oxygen. And then finally, the strongest winds of the solar system are found on, and the majority of you thought it was Jupiter. Neptune may be next. Oh, and apologies, I was not sharing the results with everyone. That was very mean. You should all have a chance to take a look at those results. All right, so take a look through those results, and we're going to kick things off in just a moment here. In fact, I would love to welcome our speaker this evening. Mirka, can you
Hi.
hear me okay? And I
Yep.
think I can
Can you
hear
hear me?
you. Yeah.
Fantastic.
All right, I'll stop sharing these poll results. And without
Okay.
further ado, would love to hear about weather. I mean, we hear about weather on planet
Elsewhere.
Earth all the time. Let's hear about it elsewhere.
Excellent. Thank you so much for having me here. As Brian said, my name is Mirka Zapletal, and I'm the Director of Education at the McAuliffe-Shepard Discovery Center, which is in Concord, New Hampshire. We are a space, aviation, technology, and earth science museum. I would tell you that we lean more toward the space and aviation than some of the other things. And we have a planetarium as well. And so I'm here to talk to you about crazy weather that you find off of planet Earth. And I think you'll agree with me by the end of this that there are some amazing things happening all across the solar system. And I will hit every one of those questions there. I will tell you that if we went with audience voting, you guys are 1 for 3 at the moment. And if I don't mention each one as we get to it, please remind me at the end. So what I'm going to do first of all is I'm going to start by sharing my screen so that you can see my presentation, and we will get going from there. Okay, so hopefully you can all see a gigantic sun is what it is.
Yeah, looks great.
And so we're actually looking at the sun right here in multiple layers. The vast majority of my images come from NASA because they have amazing stuff, but I had to label because there's one from NOAA too in there. But what we're looking at is coming from the Hubble. And you're seeing a couple of different types of light basically filtered in. And so I'm going to talk about this, how we view the sun, how we view other things as well as we go through it. But we have to start this journey by talking about here. So I went to the record books to look for some information, and some of this is probably familiar to you, but if we're talking about the strongest winds on Earth that have been recorded, so the previous record was 231, which was at Mount Washington Observatory. And then in 1996, an unmanned station in Barrow Island, Australia, registered 253. The hottest temperature recorded on Earth is a really interesting situation. So Death Valley registered 134 degrees Fahrenheit in 1913, but the value is questioned because other values around it were not nearly that hot. So maybe it was 131 in Tunisia in 1931, but that one's also kind of questioned. So it could have been 130 in this past August in Death Valley. They're still looking into it and certifying that one, but at least we know that in 2013, in 2016, in 2017, and in 1942, places around the Earth have registered 129 degrees. So we know it's at least 129, possibly as high as 134. The coldest temperature recorded, negative 128.6, which was in Antarctica. The greatest temperature range, so the greatest difference between the lowest temperature recorded in a location and the highest, is in Russia, where we've got 190.4 degree difference between their coldest temperature, which is from 1885, and their hottest temperature, which was from this past year. And then I threw in a couple of other things that you might not be as familiar with. The heaviest hail, like single piece of hail recorded, was in Bangladesh in 1986. It was a little over a kilogram. So just for comparison, a kilogram would be about 5 mangoes put together, or about 10 lemons put together. And the longest lightning bolt recorded on Earth was in Brazil in 2018, 440 miles. So to give you a sense of that, that would be roughly driving from Boston to DC. Okay, so that's where we're starting. That's crazy weather on Earth. And so now what we're going to do is we're going to take it out of our own atmosphere and go from there. And for us, our weather really comes from the sun. And so we're going to start with the sun and then work our way out from there. So we've got all of this heat, this light energy coming, and this light energy unevenly heats the surface of the Earth, right? So land heats differently than water, those kinds of things, and we end up with weather. But the sun also sends us some other stuff too. So it's not just this light energy. There are solar flares. And so if you look over on the left-hand side of your screen, there's this fantastic picture of a flare. We would actually call this a coronal mass ejection, which is a ton of plasma with its own magnetic field, essentially erupting off of the surface. Some of it falls back in, pulled by the sun's gravity, but some of it just keeps going. And these solar flares and these CMEs are very important for a number of reasons. As I said, they have their own magnetic field, and that actually expands as they travel. They also carry a lot of energy with them, which is important. They can travel pretty quickly. Some of them will take days to reach us, but the fast ones, 15 to 18 hours. So they're moving very quickly. And because they've got their own magnetic field, they can definitely mess with our electronics. They can mess with other things as well. And then there's also what we call a solar wind. I mean, most people know about flares and things like that, but there's also a solar wind, which is this steady stream of particles. And when I say steady, that's a relative, I mean, it can get faster, it can get slower, but it's constantly happening, anywhere from 300 to 900 kilometers a second, depending on the sun's activity. And this is just particles going and going and going. And how many flares we see, how fast the solar wind is moving, that really depends on what's going on within the sun. The sun has basically like an 11-year weather cycle or sunspot cycle, where we see periods of higher activity, periods of lower activity. And so that image from NOAA that's down on your right is showing you several different ways of looking at the sun using different light, essentially. There's ultraviolet is the really blue right there. The reddish, we're talking about infrared, some other ones in between. In all of these, darker is cooler and lighter is hotter. So you can see that these pictures were all taken at the same time. And there are some similar features in each one. Like you can see some areas are always dark or always light. But if you notice, there are other things happening in one and not another. And that's because we're also looking at different layers of the sun. We're still figuring out why certain parts of the sun are hotter than others. And we're figuring out how energy is moving within it. But there's so much happening here. And when it leaves the sun, it absolutely impacts us. Those solar particles that I mentioned, they are streaming toward us all the time. They include radiation, which can definitely damage living creatures. They also, as I mentioned, can mess with electronics, but we are lucky, we have a shield. And our shield is our magnetic field. So here's a picture. This is a simulation because we can't really get a picture of it directly. But if you notice, the solar wind is so strong that it's actually changing the shape of our magnetic field. It's pushing on one end. So we've got this bow shock push in, and then it's streaming out the other end as those particles keep pushing away. And so our magnetic field does fantastic things to protect us. It also channels those particles. And so if we're really lucky, it'll channel those particles in just the right way so that we get to see the aurora. And this time of year is a great time of year to see it. Some people tend to ask, is that because there are more in the winter? And that's not the case. These are happening all the time. Aurora are happening all the time, during the day, during the night, all throughout the year. It's just that nights are longer, so there's more darkness, and we can have some really, really clear nights in the winter, so they're easier to see. Is really what's going on there. So these solar particles streaming away, plus the flares, plus the coronal mass ejections, and it hits planets, it hits moons, it does all sorts of things. And so we're going to start our tour with the closest planet to the sun. And I gave them each a little tagline because I was having fun with this one. So Mercury. Mercury is a really interesting place for a number of reasons. Because it's so close to the sun, it really gets the hit of that solar wind, but also the magnetic field traveling with particles. It feels it in ways that other planets don't. And so when we look at Mercury, we are essentially seeing the surface. There is an atmosphere, but it is very thin. And because it's constantly being hit by solar particles and light, it is actually being stripped away continuously. Now, I asked in our questions, in our poll, what is not found in the atmosphere of Mercury. And so Mercury has sodium, calcium, potassium, oxygen, and magnesium. It does not have argon. That was the correct answer for that one. But I want you to think a moment about these things. Okay, so oxygen we know of as a gas, but I want you to think a moment about how we experience these other elements, right? Think about calcium, potassium, magnesium, and sodium. We don't usually breathe these things by themselves, right? There are gases that might include sodium. There are gases that can include some of these things, but we don't just generally have calcium hanging out in our atmosphere, but Mercury does. And that's because the crust itself is kind of being stripped away. The atoms of different elements in the crust are being pulled away on a regular basis. There are different reasons for each one. Some of them are getting hit with the light energy itself, the photons. Some of them are being hit by the solar particles, that kind of a thing. But we're actually seeing that these elements move and then be lost in a gigantic tail. And that image down at the bottom there is the the sodium tail of Mercury. If you could see it, it actually kind of glows orange if you were looking at it through the right kind of filter. And so you can see how it's being pulled away. That blue circle is the planet. And that solar wind is just moving everything out. Oxygen is a really interesting thing to be found on Mercury, and it is kind of key here because oxygen is very reactive, right? If we leave oxygen and water together for a while, we can get all sorts of things like rust and stuff like that because it's very reactive. Which means that if oxygen is in a place, either it has to be respired, like coming from a plant, or there has to be some other source. It has to be replenished. And so in Mercury's case, it's actually the solar wind that is constantly pulling oxygen out of the crust and into the atmosphere, and then sweeping that atmosphere away. Because Mercury has such a thin atmosphere, it's not good at holding on to the heat from the sun, which means it bakes for the side turned to it. So it can be 800 degrees Fahrenheit. But as soon as it starts to turn into shadow, it loses all of that heat and can drop down to -300. So I want you to imagine a place where your high and low temperatures, granted, a Mercurian day is 59 Earth days, but still, where your high and low temperatures swing over 1,000 degrees. You know, that's what we're talking about in terms of a day progression on Mercury. And Mercury is hot, but it's not actually the hottest, even though it's the closest. So Venus, I asked the question, which planet is closest in size to the Earth? And the majority of you got that one, that it was Venus is the closest. And Venus is pretty similar to Earth in a number of ways. Now, for those of you who look at my picture of Venus right here and think, yeah, that's exactly what I was thinking in my mind, you're either really well informed or you're lying. Because this is not what we see most of the time when we see Venus. Most of the time, what we see is the atmosphere. Here's an image of the actual planet itself. Venus has volcanoes. It has all sorts of craters, valleys, things like that happening. But most of the time, this is what we see. And that's because the atmosphere is so thick that we can't see through it. And that's mostly carbon dioxide and nitrogen. And in fact, the very first color pictures of the surface we received in 1982 from the Soviet Venera spacecraft that landed. It sent back images, and Venus is such a harsh place, as I'll explain in a moment, that it survived 2 hours to transmit information, which was actually longer than they thought it would make it. They figured a half an hour tops, but it made it 2 hours and it got us some amazing images. And now there have been orbiters that have gone into the atmosphere and then out again, gotten really good views from outside. But there have been no landers on Venus since 1982. And the reason that Venus is such a harsh place has to do with that thick atmosphere, right? These are greenhouse gases. When we think about carbon dioxide, that's a greenhouse gas. So there's actually a runaway greenhouse effect here. And those thick clouds hold the heat in really, really well, so that depending on the reading that you're getting, you can get anywhere an average temperature from 840 degrees to 880 degrees Fahrenheit. So this is the hottest place aside from the sun when we look at our solar system. And in addition, there are some pretty intense winds. Venus is really interesting because it rotates really slowly. Like, it actually takes longer for it to do a full rotation on its axis than it does for it to go around the sun, which is crazy and when I think about it. And yet the clouds go every 3 days, which means those clouds are just whipping around and whipping around. And those clouds, because of the carbon dioxide and some other gases that are in there, things like that, these clouds rain acid, specifically sulfuric acid a lot of the time. So if you can imagine a place where it's over 800 degrees and it's raining acid, that explains why the Venera spacecraft, no one thought it was coming back, and they were just hoping for a half an hour of use because it started melting and being corroded immediately as it went through this. So Venus is intense. As we get a little bit farther away, things start to change in terms of temperature. I'm gonna pass on us, because we've already talked about us a little bit, and move on to Mars instead. And so Mars is an interesting situation. We know a lot about Mars, more than we do about many other planets, just because we've successfully sent robots there, a number of them. And there's another one on its way that's going to be landing in just a few months, which is very exciting. But Mars is an interesting situation. It's about half the size of the Earth. It doesn't have a very thick atmosphere. And as scientists and engineers at NASA have said, it has just enough atmosphere to be a problem, because it's there and it can do stuff, but it's not developed enough to act the way that we would think of an atmosphere. So if, for example, you're trying to land a rover, the atmosphere of Mars is enough to heat up everything so that you need a heat shield, but it's not enough to actually slow it down as it's coming through the atmosphere. So it presents all sorts of challenges. And this thin atmosphere that has lots of dust on the ground, you end up with some really impressive dust storms. Now, I put here that the maximum sustained winds are around 60 miles per hour. So that doesn't seem really impressive if you think about it. It certainly doesn't compare with our tornadoes or things like that. But the reason it's such a low mile per hour count is because the atmosphere is so thin. You know, it really has to work hard to get moving that fast. And these dust storms are common. They can be really high. You can actually see some examples. Here's a dust devil right there. And then we've got some other dust storms moving around there. Every few years, every 2 years or so, these storms actually will go planet-wide. So if you can imagine a dust storm so big that it encircles an entire planet, that's what we're talking about in terms of Mars. And this picture down here, this is from Curiosity, one of the active rovers right now. And so you're seeing that between June 7th and June 10th, a dust storm moving into the area. And it's not only that there's kind of a different color in the atmosphere, you know, because of all that dust, but it also kind of smooths out the terrain. If you look very carefully, you'll notice that there are more ridges in the June 7th on the ground than there are over in the June 10th. And that's because of all that dust being moved in. So the dust is a challenge. I mean, we're not talking about crazy winds, but we're talking about dust on everything. And if you're, I don't know, some sort of machine operating with movable parts, dust is going to be a problem at a certain point. And part of that could be getting into joints and wheels and things like that. But part of that has to do with your power source as well. And so it creates problems for everybody, including this guy right here. This is a selfie taken by the rover Opportunity. And the Mars rovers have been amazing. I mean, we tend to send them there and say, 6 months, 2 years. And then like 9 years later, they're still going and doing an amazing job. But Opportunity was running on solar power. which absolutely makes sense in a place like Mars, because you're not really talking about huge clouds. You're not talking about these storms coming through necessarily, or rain or precipitation, anything like that. You can angle yourself to the sun, and that's great until you get covered with dust. And so 2 years ago, a big dust storm covered Opportunity's solar panels. And the engineers felt, or they hoped, that if they shut down Opportunity, or Oppie, who had his own social media, I'd like to point out, if they shut down Oppie and simply waited out the storm, they then waited for the sun to come back, it would be able to recharge the batteries, they get everything going again. But it became clear after weeks of trying to get in contact with Oppie again, that there was simply too much dust. Probably the solar panels got completely covered. And so it was never able to recharge. So, you know, it's not what I would consider to be like the worst weather in the solar system, but depending on what you're working with, it can absolutely mess with everything. And if it's a planet-wide dust storm, there's no place for you to go. It's not like you can say, well, I'll hang out over here because the dust doesn't come. No, it's everywhere, right there. So far, we've been talking about the rocky planets. So they all have this really solid core and a real surface that we can talk about and where this weather can happen. But now as we move even farther away, these are all going to be our gas planets instead, or ice and gas planets. And so the weather there becomes totally different. And the way that the planet experiences it really changes as well. So probably when people think about big storms, not on Earth, Jupiter is probably where they're thinking, where they're going in their minds. And Jupiter is a really interesting planet. It is mostly hydrogen and helium. It is gigantic compared to us. And you can almost think of Jupiter as a star that didn't make it. It has the right components, and it got big, but it didn't get big enough. So if it had been able to accumulate more hydrogen and helium and keep going and growing and growing, if it got about 80 times bigger, we would have had a double star system instead of what we have right now. So you can kind of think of it as, you know, not quite a star, but on its way when it was originally forming. And so it really doesn't have much of a surface. I mean, it's true that there is this kind of inner core, but for the most part, when you talk about Jupiter, you are talking about atmosphere. You are talking about gases, and that's why they're called gas giants as we get out here. And so when you look at this picture, which I think is beautiful, it's one of our clearest and it's one of our most recent pictures of Jupiter from the Hubble right here, you can see these gorgeous stripes. And when you look at those, you are actually looking at winds going in opposite directions. So Jupiter is huge, but it spins so quickly on its axis. Daytime plus nighttime on Jupiter is less than 9 hours. So if you can imagine that you've got 4.5 hours of sunshine and 4.5 hours of darkness, and that is just going and going and going and going, it helps explain why those winds are just going and going and going. And it's what creates these beautiful stripes. You've got winds going in one direction and then the other, and then the other, and then the other. And it helps create these beautiful storms as well. So I want to show you how the storms move so that I can talk about what is causing that to happen. So the way that I'm going to do that is, first of all, I'm going to do a different share. So just give me a moment right here. Okay, so we're looking at the great red spot right here. This is going to be time lapse. It's not so much a video as NASA putting together a number of different frames so that you can see how it's moving. And it's very short, but I just want you to see that movement, okay? So you can see how it's rotating. You can think of this as a hurricane on steroids in some ways, okay? That's what we're talking about. It is an anticyclone, which means that it's going in counterclockwise direction right there. But that's what we're seeing. And if you look on the picture of Jupiter, so hold on a second, let me go back to my presentation. Hold on a second, there we go. If you look on the picture here, we've got lots of other little circles, if you look. you'll see that there's one there and there's another one there and there. There are all sorts of like little marbles or pearls. Those are all individual storms. Most of what we are seeing right here are anticyclones. They're all pretty much going in counterclockwise, okay? And they can get really, really fast. They can have sustained winds of 400 miles per hour or more. Okay, so we are talking about really intense storms. What's fascinating about Jupiter, because it has no land really, those winds can just keep moving and moving and moving. Now, Jupiter has these anticyclones, but it also has cyclones. So storms that are going clockwise. The thing is, we're not really seeing them in this particular image. I'll show you a different one in a moment, but we're not seeing them in this image right here. Jupiter is amazing on so many levels, but the great spot is in of itself phenomenal. So we know that at least in 1831, an amateur astronomer actually saw this and made a comment, recorded this big red swirling storm. So we know at least at this point, wow, almost 190 years, right? However, in 1665, the astronomer Cassini made a comment, and then several years later, again, so for several years, made this comment about a persistent storm. So entirely possible that this storm goes back hundreds of years. So imagine that, first of all, a storm that can last for hundreds of years. Then its size. I don't unfortunately have a picture of the Earth to compare it to right now, but I can tell you this, it's bigger than our planet. Since we've been observing it, at least since 1831, it's gotten as big as 4 times the size of the Earth. So imagine that, like a storm that can swallow a planet, no problem. But it's also gotten smaller recently. In fact, quite a bit smaller recently. In the last few decades, it's gone to 1.5 times the size of the Earth. And so now it's actually just a little bit bigger than we are. Still gigantic, right? But definitely smaller. And so this brought up all sorts of questions like, are we losing it? Is it going away? Is it dissipating? Things like that. And the answer is no, it's not going away. You know, definitely it's changing shape and size, but it's still there. And the answer has to do with the cyclones that go along with it. So I'm going to bring up another image. This is actually looking at cyclones at the pole of Jupiter. But if you notice, we've got some beautiful swirls. Swirl, 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 all of these gorgeous cyclones all going clockwise. But if you look on the edges, you'll notice right next to them going in the opposite direction, like this. So Jupiter has a really well-developed atmosphere. What that means is that there are layers, like the Earth, right? We have multiple layers in our atmosphere. We have the mesosphere in the middle. We have the thermosphere, things like that. Jupiter's got layers. Based on what we can tell, the anticyclones are usually in one layer and the cyclones tend to be in another layer. So we don't necessarily see them, but we can see them interacting when a storm gets pushed in a certain way. Or in the case of the Great Red Spot, as it gets smaller, it's because we think there are cyclones on the side of it, kind of moving it and squishing it and peeling some of those clouds away. So Jupiter has just weather that keeps going and going and going. It is a gigantic set of storms. And so when we kind of think about our big storms, you know, which can be gigantic and terrifying, on Jupiter, they are so much bigger and quite a bit faster as well. Jupiter has some other really interesting weather, but for some of those features, I really want to focus on Saturn instead, which has similar weather kind of taken to an extreme. And I called Saturn strange shapes and lights because there are things there that are like, what is that about? So I'm going to start off by talking about the hexagon, just because, I mean, it's weird. And so once again, I'm going to switch what I'm sharing because I want you to see this image. So this again is a NASA time lapse. It's not a video, it's several different frames that they kind of stitched together. This is called the hexagon, okay? The hexagon is this band that goes like this 6-sided jet stream. That's what this is right here, okay? This is a 6-sided jet stream, which is keeping a big storm in its center. So we have a 6-sided storm surrounded by a 6-sided jet stream. We have no clue why there are sides, We don't know why it's not this really nice ring, right? What is it that's making this happen? We're not sure. We just learned last year that this storm in the middle is much bigger than we thought. We had kind of assumed that it was just in one layer of the atmosphere, and we now know that it's probably over 150 miles tall. Like it is a massive storm just at the pole going around with 6 sides. If you can explain it, fantastic, because at the moment we can't. So there's that. It can get really, really windy there too, so that upper level winds, once again, a well-developed atmosphere can reach, 1,600 feet per second, so fast winds. And then this other picture that I'm showing you right here, Saturn has aurora, just like us. And you can actually see this is a set of images where we see the aurora move its way around. Jupiter has aurora too. They're not, to our knowledge, they're not quite as intense, or at least we can't see them as well as the ones on Saturn. We know that sometimes these are kind of timed with our aurora, so it would make sense that it's the solar particles, but every now and then Saturn just kind of lights up on its own, and we're not entirely sure. We know that it has a strong magnetic field, so obviously some particles are moving around, but we don't know exactly what's happening. It's just suddenly got these amazing lights at the poles. And Saturn also has impressive storms, not quite the same as the Great Red Spot, but amazing in their own way, so that we know of at least one lightning storm that lasted at least 7 months. And so we know that these really high intensity electrical storms on Saturn just keep going and going and going and going. And so think about our weather. We can have big systems, that come across North America, and they'll stay together, but usually at a certain point, as they encounter the Atlantic, as they get across the Atlantic into other situations, they start to dissipate, and then they'll fall apart. Whereas in Saturn, once again, there's really not land there. If you tried to land on Saturn, you would just kind of float in a really high pressure environment. Saturn is really gas, even more than Jupiter. And so Saturn is actually very, very light for its volume. The density is really low. If you had a bathtub big enough and you dropped Saturn into it, it would float, because its average density is actually less than that of water. So once again, there's no land. This stuff can just keep going and going and going for quite some time. Now, Saturn has something else that's pretty interesting. Saturn has a lot of moons. And one of those moons, maybe is kind of close to us. So Titan, we're really curious about Titan because it has a well-developed atmosphere like us, mostly nitrogen, once again, like us. Surface pressure is greater, 50% greater, but, not crazy the way that it is in Saturn and Jupiter because of the masses of those planets. And because Titan has a tilt, it does have seasonal changes. What we can see in terms of scanning the ground, it clearly has lakes, it has rivers, it has oceans full of liquid. This is it. This is so like Earth, except it is so far out and so cold, it is not raining water, it's raining liquid methane. So here's another example of, it seems familiar, but it's definitely doing its own thing. So just kind of imagine, instead of a water cycle, there's a methane cycle. There is also water ice on Titan, but when we talk about kind of the actual precipitation, what's filling those lakes and rivers and oceans, it's liquid methane instead. So, similar but different. Once we get past Saturn and Titan, we've now moved through what we call the gas giants, and we've gotten into an even colder space. So that now we start talking about ice giants. And Uranus is the first ice giant that we hit. When we talk about it, it's still a lot of gas, it's a lot of helium, it's a lot of hydrogen. The color that we get in kind of that greenish, bluish color, that's coming from methane in the atmosphere right there. But it's much colder, so there's a lot of ice present. And the picture itself is not at a funny angle. The planet is at an interesting angle. So our axis, if you think about the Earth, we tilt about 23 degrees. That tilt is so important to what we experience as a planet. That tilt is why we have seasonal changes. So as the top part is angled away, we're getting less light up here and more down toward the south. So we have winter and summer. And then as the top is angled toward the sun, we switch, summer in the north, winter in the south. That tilt is what gives us seasons. A planet like Jupiter that really doesn't have a tilt, you know, its axis is basically up and down, doesn't have seasons. It just has day and night, whereas we have seasons. Uranus has taken it to the next level. Its axis is at 98 degrees. So it's basically lying on its side, as the picture indicates. That means that it's not just that it has seasons, it's got like crazy seasons. It's got seasons that we can't even imagine, to be honest. It takes 84 years for Uranus to go around the sun. Because it's on its side, during summer at one pole, it is facing the sun the entire time. And then the other pole is facing away. And then they switch as they go around, okay? So for 21 years, one pole is facing the sun continuously. And so it is summer and it is day for 21 years. And then when we get to winter, it is winter and it is nighttime for 21 years, which in of itself is crazy to think about, right? I mean, this really is like Game of Thrones. Winter is gonna last for a really long time here. But during the spring and the fall, when it's making that transition, Uranus actually rotates every 17 hours. So then the day plus night is 17 hours. So imagine that for 21 years it's darkness, and then suddenly you're going through about 9 hours of light, 9 hours of darkness, 9 hours of light, 9 hours of darkness, and then you go back to 21 years of light. Like it's that kind of extreme. So Uranus is in a kind of a class all by itself as a result of this. It's incredibly cold. Negative, different readings, negative 370-ish. I've seen 373, I've seen 371, but let's just say 370-ish, which is incredibly cold if you think about it. The other thing that makes Uranus a little interesting are there's high concentrations of hydrogen sulfide, so that the planet itself actually smells like rotten eggs. So in addition to dealing with crazy cold, extreme darkness, and extreme light, it smells really bad too. Neptune has some similar situations when we look at it. It is another ice giant. It's also really, really cold, roughly about negative 370 again. But there are some other things happening when we look at Neptune as well. So first of all, it actually is giving off heat, more heat than it's getting from the sun. So we know that stuff is happening on the inside. We know that there's some sort of internal heat source, which creates some really interesting situations as well. But if you look on this picture right here, you'll notice it's a very nice blue color. It's very similar to Uranus, mostly helium, mostly hydrogen, but the blue comes from the trace gases, different distribution of trace gases. This dark area right here, that's one of the storms. It, like Saturn, like Jupiter, Neptune can get some pretty big storms. They last for several years, usually 2 to 4 years. They tend to show up as a darker area. What really sets Neptune apart in terms of its storms is it does have the highest wind recording. Jupiter, as I said, could get up to 400 miles per hour. On Neptune, for our storms, we're talking about probably 1,200 miles per hour. So think about our highest wind reading, right, on Earth. 254. I'm going to say 250 because this is a little easier for me to do the math. Multiply that by almost 5. That's what's happening on Neptune. So they are incredibly intense storms with amazing winds. And then, because of what's happening in the lower atmosphere, and you've got this heat source and you've got a number of other things happening, there's not really rain. And I said more like hail. And when I said hail, what I meant was imagine diamonds raining down. That's what we're talking about. Now, this was theoretical. The idea that diamonds could be created if you had the right combination of temperature and pressure to kind of make that carbon crystallize and stay together. And then a few years ago, using one of the newer laboratories for particle acceleration and controlling conditions and things like that, researchers were actually able to create it, like just for seconds, just for a moment. They were able to get the right low temperatures plus pressure, all of that together to get diamonds to essentially like crystallize out of the carbon. And then they disappeared because they couldn't sustain in the lab. But in Neptune, which is a planet that can sustain it, this is going to be a really slow process in that lower atmosphere, in that interior, so that we think probably these diamonds can grow and grow and grow and grow, possibly as big as a meter across. So imagine now a place where you've got crazy winds and gigantic diamonds falling down. That's what conditions are like when you get toward that interior of Neptune. Both Uranus and Neptune are cold, but they're not the coldest. That honor belongs to Triton, which is one of Neptune's moons. Triton is another interesting case. I know I keep saying that. I know I keep saying that every planet or moon is really interesting, but they are. It has a very thin atmosphere, not much in the way of gravity when compared to Earth. And it also has what we call a retrograde orbit. And a retrograde orbit means that it's orbiting in the opposite direction to other things. So every other moon that we know of around Neptune is going in one direction and Triton is going in the opposite direction, which is an interesting situation. It gives us the idea that Triton was not originally there. Probably Neptune formed, its other moons formed, and some of them are probably pulled in as well. Triton was probably what we would call a Kuiper belt object. So that's an area farther out even than Neptune, was probably an object out there and then got close enough to Neptune for Neptune's gravity to pull it in, but it was already traveling in a certain direction. And so now as it's been pulled in, it's moving in a different way than the moons of Neptune. Triton is actually getting closer to Neptune a little tiny bit every time it goes around. So, I mean, we're talking millions of years in the future, but at some point we expect it to crash into the planet because its orbit is not entirely stable. Now, in addition to being this unusual object going around Neptune, it is also incredibly cold there. This is the coldest reading that we've had so far in the solar system, negative 391 degrees Fahrenheit. So when we're talking about what is true cold, this is the place where you would go, although I don't think you would want to go there. That's not fun. Now, I've taken us through the planets. We've also hit 2 moons, but I'm going to throw in one more just because this is a place that's near and dear to so many hearts. I'm not going to get into the whole planet, dwarf planet thing right now. I just want to tell you a little bit about Pluto. Pluto is something that is a place that we're still really learning about. Certainly the New Horizons flyby in 2015 has added tremendously to what we know about it. So we're still figuring out, this is one of the new images that came from that. But what we've learned, if you look at this picture of Pluto, you'll notice that there's kind of like a heart shape right here. And in fact, it's oftentimes referred to as the heart of Pluto. This heart, especially on the left-hand side, is pretty much nitrogen ice. You're looking at gigantic nitrogen glaciers. It's actually filling kind of a depression. And this ice right here, this nitrogen ice, is such a huge mass itself that it's actually reoriented the planet slightly because it's made it heavier in a certain spot that's kind of turned it a little bit. And so we know there are glaciers. We know that they're expanding and contracting. We know that they're moving across, building up a lot of mass on one side. There are also cryovolcanoes. So we're talking about volcanoes that actually erupt like ice and icy fluid coming out. And then this heart right here, this nitrogen. So Pluto is in a situation where it's so cold, it's so far away from the sun that it's getting sunlight, but it's kind of like seeing a bright full moon. It's really not getting much heat in that respect. But there is a bit of a difference. So daytime and nighttime do have slightly different temperatures. What that means is that when it becomes nighttime, the nitrogen in the atmosphere, it actually gets cold enough for it to condense and fall as ice and snow. So the atmosphere falls down at night. And then when daytime comes, it will sublimate back to gas up to become an atmosphere again. And so there's this daily cycle, right, of condense into ice, sublimate into gas. And as this is happening, it's actually creating these, I'm not going to say planet or dwarf planet, these Pluto-wide winds that are being driven by that up and down movement of the atmosphere. So this is an atmosphere that disappears and reappears continuously because of where Pluto is. So we've just done a crazy tour of the solar system. I just want to take us back to those stats that I started us with. Okay, so strongest winds in the solar system, not us. That's Neptune. Hottest temperature, not us. That's Venus. Coldest, not us at all. That's Triton. Greatest temperature range. You know, our range was like 190 degrees. Mercury's closer to 1100. Heaviest hail. Remember, our heaviest hail was like 10 lemons put together, okay? Versus meter-sized diamonds on Neptune. Longest lightning bolt. I searched and I searched. We don't have the longest lasting lightning storm, but I could find no statistics at all on longest lightning bolt. So I'm claiming it for us, at least for the moment. We've got something until I'm sure at some point we'll, learn something else about another planet. But at least for the moment, based on everything I could find, we've got the longest lightning bolt. So I know that this was a very rushed tour, but hopefully you got an idea of just how extreme the weather is in other places. Before I get to questions, I just want to say, if you need more space, we are here for you. You can go to starhop.com to check out our blog, get more information, find links to some of the stuff that we've done in terms of presentations. You can also come and visit us. We are open, masked, and cleaning frantically every few hours. But we also host a monthly virtual Superstellar Friday event. In fact, ours was just last week, and Brian told us all about the science of nor'easters just in time for us to have a nor'easter. So the planning was amazing. But we would love to have you visit either virtually or in person, depending on what you're interested in. And with that, I am happy to take some questions. I just wanted to leave you with another picture of Earth. So this right here was taken by astronauts on the ISS. You're looking at the eye of Hurricane Dorian. So all of the clouds around are that the upper level clouds of Dorian, and then we're seeing down into it. And so I will stop my share there, and I am happy to answer some questions. My best. I'm going to say right now, I'm not an astronomer. I'm a science educator. So if I can't find the answer, I will do my best to find it for you.
Thank you so much, Mirka. That was excellent, excellent. And questions. Yes, we have already lots of questions. And if you do have questions for Mirka, please go down to find your toolbar in the video screen. Just go down to the Q&A button and get your questions in there. We'll get to as many as we can. For those that we can't get to this evening, you can contact, probably the easiest way would be to contact me directly, education@mountwashington.org. Again, education@mountwashington.org. And we can try and get those questions over to Mirka, because we have clearly a very educated and smart, and I'm sure very good looking audience too, though I can't see you all out there. So let's just see if we can get through a number of these, including from the beginning. Okay. How does Jackson and a couple other people wondered, how does one measure the length of a lightning bolt? Do you have any idea?
So that I don't know. I believe that they've had to have used satellite imagery in order to make it happen. I don't see any other way that they could have done it. Now, I saw some pictures, some images of it, but the images were from the ground. So I think that there had to have been a series of pictures. Guinness Book did certify that, but before that happened, the world, I always get this wrong, the World Weather Meteorological, that's what it is. The World Meteorological Organization did investigate and make sure that all data points were accurate. So, but I'm assuming you would have to have some sort of satellite image to back up that it's a single bolt instead of multiple, across a range.
Yeah, and so sort of similarly, there are a number of questions, and in fact, a question I had myself in terms of the measuring of these statistics, not only on Earth, but elsewhere.
It's
So, I mean,
hard.
there have been questions from a few folks in terms of, so things like temperature or wind speed, or perhaps some of these other variables you mentioned. How are
So
those sensed?
yeah, so there are a couple of different ways that we can do this. I mean, the highest tech would be like, let's send something there and see what it finds, right? That would definitely be the highest tech. And especially when we get farther away. Like our information about Pluto really is coming so much from New Horizons right now, just because it got the closest of anything that we've had, and it sent back such phenomenal information that they're still going through. So that gives us, I would say, the most accurate readings is if we can be there. And we have sent things like Galileo orbited Jupiter for quite some time, collecting as much information as it could. Right now, NASA's working on something they're calling the Dragonfly, which is going to basically be like a flying probe that can go into Saturn's atmosphere and collect information and send it back to us. We've got all of the rovers on Mars. One of them isn't even a rover. I call it a rover, but InSight is actually stationary. It's drilling down into the planet. So that's one way to do it, but that's expensive. Just getting it off our planet is such a risk, and then getting it there is like such a risk. It's crazy. So there are a couple of other things that we can do. We can just set up satellites that kind of collect information. If, for example, we know let's say the size of the Great Red Spot, we know how wide across it is, and then we can basically like follow a point and see how it's moving around that diameter. We can calculate wind speed. So that's one option that we have. We can also use infrared and things like that. And then I'm sure there are a lot of equations that run into some of this because you're trying to replicate it. So I think there are a number of different things. Some of it is remote, some of it is on the ground essentially. And then I think that some of it is probably taking what we know about Earth weather and then projecting it onto what's happening in the planet.
Yeah, I'm sure some of the direct measurement of these variables you mentioned, we may not have the technology for. We have a hard enough time on Mount Washington designing anemometers that'll withstand high
Right,
wind
exactly. I
speeds.
mean, think about that. And you don't even have to, like, that's like the final hurdle, right? Is getting it to work over there. And there are so many other crazy steps. People tend to think that going to these places is easy because we've done them. Oh, it's just the moon. It's just 3 days away. It's not oh my gosh, just last year alone, 2 different craft crashed on the moon, unmanned, but like they made it so close and they lost it at the last few seconds. So it's still so hard. So definitely using some of our digital, telescopes that are in orbit around us, like Hubble and Kepler and things like that. They help us get some of that imagery. But their resolution's only so good. So some of it is definitely, I mean, the diamonds in Neptune, those were hypothesized. We thought that they should exist, but it wasn't until in the lab that you could prove the concept. Okay, now it makes sense. So.
Right, so at least theoretically possible.
Right.
All right, we have a question from James, and I think I'd heard some scuttlebutt about this as well, about some geomagnetic activity, perhaps some aurora maybe coming up in the next few days. I don't know if you have any info on that.
I do not know that. I mean, it's certainly, we are in a low sunspot cycle right now. So if you're talking about, I mean, obviously winter is better viewing, but the next higher activity is going to be in about 5 years. We're actually kind of at the low point right now in terms of sunspot activity. So I know that NASA will, not necessarily themselves, but will pass along the information so that you can get the alerts. Typically, we would know a day or so in advance, a couple days in advance, possibly. But I don't actually know what's coming up recently. I haven't checked.
Yeah, the University of Alaska Fairbanks, their Geophysical Institute, has a good aurora forecast, and I'm sure there's a variety of other resources as well. Yeah. All right. Oh, lots of questions. Apologies, everyone. We won't be able to get through all these, but this is a good question. It comes from Donna. She's wondering, because you mentioned sort of the relative thicknesses of different planets or moons, including Earth's. How would you classify Earth's atmosphere in comparison to the rest of the solar system?
We have this is one of those really frustrating things that we use the term well developed all the time without actually talking about what that means. But Earth's atmosphere is really impressive, actually. What we have is, we have not only an atmosphere, meaning that there is gas around our planet, but we actually have multiple layers of gas, so that what's happening in the exosphere, that outermost layer, is different from what's happening right up in the troposphere, right up against us, and things like that. So we have layers where you'll notice that winds are moving one way in one and a different way in another, and stuff like that. So our atmosphere is actually really complex in comparison to some of them. And then around our atmosphere, we've also got our magnetic field, and not all planets have a strong enough magnetic field. They usually all have something, but it totally depends on their core and stuff like that. So that what we have is actually kind of unique, our combination.
Interesting. Yeah, it's really interesting to compare, and certainly Earth's atmosphere complicated enough in comparison.
Right. And it becomes even more complicated when you think about a place like Jupiter or Saturn, which is mostly atmosphere.
Right.
And you can't even see it because it's so thick. You can't see what's happening underneath. So.
Oh, and there were a number of questions that did come up around some of the gas giants. I believe you'd mentioned on a couple occasions that really just a lack of any real solid surface. So is that in fact true? These are just not.
It's so weird to think about. So there is a core. There is this kind of metallic thing in the center, but around that, it's gas that has been so compressed that it's almost liquid, but it's not solid. So you'd be floating kind of in this compressed liquidy gassy thing with pressures that are so much higher than what we have. Yeah, I mean, it is like, I mean, there is this core. Jupiter has more of one than Saturn. Saturn, we think, is really kind of a weird, like, what's going on in the middle. But yeah, isn't it? It's strange because we're so used to being a rocky planet where there is a planet. And then our atmosphere is above that. Whereas for these gas giants, it's their atmosphere with something in the middle.
And yeah, very, very bizarre concept in comparison. Related to Jupiter, this was, I thought, a fascinating question from Caitlin. She asks, let's use our imagination, if Jupiter had become a star and this was a double star system, what would happen to the other planets? Would they circle around their closest star? Like, would Saturn rotate around Jupiter?
It really depends. So it's kind of similar to, if you think about it, the Earth and the Moon. Okay, so the Earth and the Moon, the Earth has much more gravity than the Moon. If you could get the right distance between the Earth and the Moon, the gravitational forces would kind of balance out. You'd be mostly toward the Moon, but you'd almost be like between them. But once you got past that point on either way, the gravity of one or the other would dominate you. So it would be the same thing with, you've got a double binary system. You'd be thinking about like two gigantic spheres around the sun and Jupiter. And so where those spheres met, the gravitational pull of each would be equal, but within those spheres, the planets would be going toward one or the other. If that makes sense.
Yeah. No, it was an interesting thought experiment for sure.
Yes.
And I believe there are other examples in other systems that, we can observe that, I suppose. The little I know about astronomy.
Right. Yeah. I mean, since we don't have one ourselves, it does make it really complicated. But yeah, there are points, there is a point between the Earth and the Moon where the two gravities kind of balance so that you wouldn't fall toward one or the other. You would stay right there. But
okay. Interesting. Yeah. Ed asks, and I'm not sure if you'd cover this, so apologies. Why does the red spot, the big red storm on Jupiter here we're talking about, move independent of the surrounding atmosphere? Is there something below anchoring it?
What it's got actually winds going in one direction up above it. It's got winds going in the opposite direction below it. So they're kind of keeping it from going up and down. And then based on what we know, we think that there are other storms we can't see on either side of it, so that it really doesn't have the opportunity to move because of what's around it.
Okay.
Yeah. If I'm trying to remember, I think that the winds to the north, I believe, are going eastward. The winds to the south are going westward. And so that it can't move up and it can't move down. And then I think that there are the cyclones in a lower level that we can't see there. So.
Yeah, a lot of challenges in trying
to
observe that.
Think of it as like each storm is a marble and Jupiter's just packed with marbles right next to each other,
Yeah, that's a good visual. Here's an interesting question. Apologies if I mispronounced the name Rohan or Rohan.
Okay.
If Triton were to collapse into Neptune, would there be effects felt on Earth?
Well, yes, but I don't think in the way, like, there wouldn't be a shock wave that we would be dealing with, or something like that. But certainly some kind of collision like that would absolutely throw off a bunch of stuff. There would be no question that pieces of material would be ejected from something like that. And some of that material would fall back onto Neptune, but some of it would absolutely get farther away. So depending on the direction, you could be looking at more meteors coming in at a certain time. You could also even be talking about some impacts and things like that. Stuff you'd probably also be able to see some of the bigger pieces getting closer to the sun. You'd see them start to vaporize, because these are gas. I mean, they're frozen, but they're gas giants. So there'd be a lot, like a comet, there'd be a lot of material there that could vaporize. So we would probably see some stuff. I don't think that it would change our world very much, but we would definitely witness some of the ripples.
Okay, yeah. Question, well, first a statement, then a question from Lisa. First off, this is so fascinating. Thank you for sharing this. Will there be more research done into Titan perhaps, and seeing if we'll be able to support life for
Absolutely.
humans if we have to
Absolutely.
leave?
There are plans to get back there, in part because I mean, it's methane, which is, for us, we're like, what does that mean? But we know that there is water there, and ice water. So we know that there are some reserves, which suggest to us that it's entirely possible that this could harbor life. And is it going to be life that we expect, which is always a handicap for us in some ways, because we imagine that life is like us. It's got to be carbon based. It's got to be dependent on water, things like that. And it might not be. But certainly Titan is one of the best candidates, we think, for harboring at least the conditions for life. So absolutely, NASA has plans, and others do have plans to see if they can land some probes there and get more information.
Yeah, I'm sure there's a lot to understand within that, the cycle, as you mentioned, not necessarily a water cycle like the one we're used to, but trying to understand how we'd function within all that methane around you.
Right.
All right, and let's see. I think we'll wrap it up here. One last question, because I know you have little ones to take care of at home, and I'm sure we all have places to be after this, or staying at home anyways. But Gary asks, how quickly is Mercury deconstructing? Do you happen to know that?
It's going to be around for millions of years. Okay. So but it's enough of a movement that we can actually see the molecules redistributing themselves. So you can see, if you're looking with the right type of spectrum, you can actually see how this change is happening. And when they're looking at the different components of the atmosphere, they can see the imbalance, that there's a lot of a certain element here and not over there, but it's being moved and stuff like that. So I mean, we're in no danger of losing Mercury, but it's being, worn away over millions of years.
Right. Yeah, and it's like you've mentioned throughout the program, it's fascinating to try and fathom these different time scales that are all relative to what we understand here on Earth.
Yeah, exactly. I mean, we're going to lose Earth too, but that's billions of years away. So we got a little time.
Yeah, I guess we have other things to worry about before then. So wonderful. Well, thank you so much.
You. And
lots of great comments.
Absolutely send me other questions. And if anyone thinks about something tomorrow, because that's the way I am, that hours later, there's a question I wish I had asked, you can also go to starhop.com and you'll find my contact information, and you can always send me an email that way too.
Excellent. Okay. So either starhop.com, look for Mirka's contact info, or education@mountwashington.org. Both work for both of us. So thank you again. Thanks to all of you for joining tonight. If you enjoyed tonight's program, please consider becoming a member if you haven't. If you're not currently one already, or perhaps if you are, consider donating to support this free program. You can do that over at mountwashington.org. And while you're there, don't forget to join us for our next Science in the Mountains program. That's Tuesday, January 12th at 7 p.m. And the topic will be the art and science of long-term weather forecasting, presented by Derek Schroeder, meteorologist at the National Weather Service nearby in Gray, Maine. And then additionally, on Tuesday, February 9th, presenter Dr. Peter Crane, who's the curator of Mount Washington Observatory's Gladys Brooks Memorial Library, will present on the very first Weather Observation Expedition on Mount Washington, the Huntington-Hitchcock Expedition of 1870 to 1871. So don't forget to register for those programs. You can see recorded programs, our previous recording programs, including this one, over at mountwashington.org/SITM. Have a great night, everybody. Thanks again for joining. Thank you, Mirka.
Thanks.
Take
Have a
care.
great evening.
Bye, everybody.
Bye.